In the last lecture of the Computational Intelligence course, we covered evolutionary algorithms in general. Now we are going to cover them in details. We will work on the n-queens problem again as the example. Remember the n-queens problem we considered last time. Here we will generate an evolutionary solution for the problem. N-queens problem is defined as place n-queens in such a way that no queen is in the way of another queen. So if you consider any column, any row, any diagonal, in this there should be only a single queen. Remember the encoding that we considered previously. The representation is such that one solution candidate is represented with a chromosome with n genes. Each gene is such that one row of the board with n possible alleles. A gene may take n possible value. Value of the gene shows position of the queen in the corresponding rank. For example, consider this solution candidate. Here we have 5 columns and rows. This is the n by n table. And here, this is corresponding to phenotype. And the corresponding chromosome is that one. This is saying that the queen in the row 0 is placed in column 3. So we have value 3 here. For the next row in row 1, queen is placed in the column 0. So we have value 0 for the next gene in the chromosome. Solution candidates with more than one queen, each rank not permitted by this representation, because we can write only one value here. There is a smaller search space that we talked about previously. As the data structure that we are going to use in the algorithm, we have a structure for the individuals which has an integer fitness value. This is corresponding to the number of collisions with the other queens. Integer n, this is the number of genes, that is number of rows in the chromosome. And we have an array here, genes n has n entries. This is genes, that is queen positions in rows. This is end of the definition of the individual represented by E and I and D. And we have another type definition for the population represented as POP. In this data structure, we have an integer size. This is the number of individuals in the population. And we have an array of pointers of individuals. So this is a vector of individuals. And we have a buffer. This is buffer for individuals that we are going to store. And we have the best individual. Again, this is a pointer. These are arrays. Now we are going to consider the main loop of the evolutionary algorithm. There is a need for the initialization of the population. Here, pop is the parameter. On that one, we are applying the initialization. While population evaluation, where pop is the parameter, is less than 0, which means that while no solution found, and generation count is greater or equal to 0, not all generations computed yet, then we are applying population select from the population pop, team size, and another parameter elitist. Select individuals, this is natural selection. So select individuals, apply on them cross operation, population cross. We have parameter pop, again the population, and this is showing, this is a variable showing what is the portion on which we will apply crossover. Do crossover, parental selection, and crossover. And then after the crossover operation, we will apply population mutate. On the population, according to some probability given as parameter, mutation operation will be applied on the individuals. Here we have some parameters, and the explanation of the parameters are as follows. Now we are going to consider the parameters used in the algorithm. Gene count is the maximum amount of remaining generations used in the loop. Tournament size, TM size, size of tournament selection. Here we have elitist. In the case if the best individual will always be taken. In the next function we have frac, fraction of individuals which will be submitted by crossover. And here there is prob. Prob is mutation probability. Here is the code for the initialization. This is create random series of n numbers from 0 to n-1. Notice here, if we select a random value by the drand call, it generates a value between 0 and 1. And if we multiply this value by n, and if we take the integer part, then we have a value, an integer, which is between 0 and n-1. We are going to use this in the algorithm. There is no return value. The name of the function is individual initialize. Here we have a pointer to the individual that we are going to initialize. Initialize an individual. We have a loop parameter I. We are initializing the genes randomly. We are setting I to individual n. This is the number of genes. Each time we are decrementing the value of I and compare if it becomes 0. If it is 0, it will go out of the loop. Individual genes, this is the array where we are storing the gene value. For the ith gene, it is set as random value multiplied by n, individual n. So we have a value between 0 and n-1 as the value of the gene I for the individual. Initially we are setting the fitness to 1. So this is saying that fitness is not known yet. And this is the end of the initialization of the individual. We need also to initialize the population. Here, as parameter, we have a pointer to a population. We have a loop variable I. For I, we are setting it to population size, that is how many individuals we have in the population. Each time we are decrementing the value of I and comparing with 0. While it is greater than or equal to 0, we will continue in the loop. Individual init is called, it is the function here, by each individual in the array of the population, in the array called INDS. So we are initializing all the individuals. This is the end of the population initialization. In the algorithm, we need to calculate the fitness of each individual corresponding to solutions. For this purpose, we are going to use negated number of columns and diagonals having more than one queen. Negated number is used due to maximizing fitness. In order to find the columns and diagonals having more than one queen, we are using a value d, which is defined as the value for gene I minus the value of gene K in the chromosome. We are taking the absolute value of this difference. Suppose the queen here in the row 4 and its position is 3, that is, we are setting I as 4 and genes I is equal to 3. And for each K here, we are going to calculate what is D. Here, the value of gene is 1. Take the difference, 3 minus 1, it is 2. So, gene I minus gene K is 2. Consider this row, the value is 4. Take the difference and absolute value, it is 1. Consider next one, the difference is 3. 3 minus 3, the difference is 0 here. If D is equal to 0, this means that the queens in row I and the queen in row K are in the same column. And if D is equal to I minus K, this is I and this is K, in that case, it means that they are in the same diagonals. Now let's consider I minus K. I is 4 and K is 3 here. I minus K is 1. K is 2. I minus K or minus 2 is 2. And for this one, I minus K is 3. And for the last one, I minus K or minus 0, it is 4. Compare D. If D is 0, let's consider where D is 0. It is 0 here. It means that the queen in row I and the queen in this row is in the same column. So they are in the same column. This is one of the conditions. The other one is compare D with I minus K. And here D is different from I minus K absolute value, but they are the same here. So this means that the queen in this row, which is here, is in the same diagonal with the queen in row I. For this sample case, for this solution candidate, there are two collisions. So fitness is equal to minus 2. If fitness is 0, it means that no queens are attacking each other. It's the solution. In that case, if fitness is 0, it is a solution. For this candidate solution, the fitness is minus 2, since there are two collisions for the candidate. Notice that if fitness is 0, there is no queen attacking another, so it is corresponding to a solution. If queens in one column or diagonal is greater than equal to 2, count each pair easier to implement. So fitness function results immediately in termination criterion. Solution has highest possible fitness, which is equal to 0. Also, termination is guaranteed when maximal generation is reached. Now we are counting collisions by computation on chromosomes. This is the function individual evaluate. We have a pointer of type individual. So this is the individual pointed by this pointer that we are trying to evaluate the fitness. We have loop variables I and k. We are going to use double loop here. We have integer d. This is the horizontal distance between queens. And we have integer n. This is the number of collisions that we are going to calculate as the fitness value. If individual fitness is less than equal to 0, remember that initially we are setting them as 1. That means that if it is 1, the fitness is not calculated. However, if it is 0 or less than 0, that means that fitness is already calculated. If fitness is already known, return individual fitness, the fitness value stored in the individual. For n set as 0, so number of collisions are set as 0, and we are setting the value of the loop parameter I as individual n. Remember that this is the number of genes in the chromosome. Each time we are decrementing I and we are checking if it is greater than 0. When it becomes 0, we will go out of the loop. For the inner loop, we are setting k to I. Each time we are decrementing the value of k by 1, and we are comparing if it is greater than equal to 0. So in this two loop, traverse all pairs of queens. We are setting d as absolute value of the difference individual genes I. That is the value of the gene I minus individual genes k. This is the value of the gene k of the individual. We are taking the difference and then taking the absolute value. So we are calculating d and then checking if d is equal to 0. If so, they are in the same column. Or d is equal to I minus k. In that case, it is in the same diagonal. If this is the case, this condition or the other condition, we are incrementing the value of n, which is corresponding to number of collisions, by 1. So count the number of pairs of queens in the same column or diagonal. At the end, after we consider each pair, we are returning the individual fitness. First, we are setting it into minus n, and after that, we are returning that value. If n is large, that means that fitness is poor. In the best case, it will be 0. This is the end of the individual evaluation. In the population, we have several individuals, so we have to calculate the fitness of all individuals of the population. Meanwhile, we are going to determine the best individual. Notice that best individual fitness is 0, means that a solution is found. This is the function to evaluate the fitness of each individual. Here as parameter, we have a pointer to population. This is a variable of population type. We have a loop variable I, and also we have an individual pointer, best. This is corresponding to best individual. We are setting best as the individual at location 0 in the array in the individuals of the population. This is the initialization. And after that, we are evaluating the value of the best. And after that, we will consider the other individuals. For this loop, we are setting loop variable as population size. Each time we are decrementing the value of I and also comparing if it is still greater than 0. If it is greater than 0, it continues in the loop. In the loop, we are checking if individual evaluation of the individual at location I results in such that it is greater or equal to fitness of the best individual. That means that this is our new best. So we are setting best as the individual at location I, this one. And in the loop, after we consider each individual, and best is adjusted meanwhile, we are setting, when the loop ends, we are setting the best of the population, whatever found here as best. And at the end, the function returns the fitness of the best individual. So this is the evaluation of the whole population.